Okay, thanks everyone for your attendance today. It is my pleasure to introduce Patrick Coles from Los Alamos National Lab. At the moment, he leads the near-term quantum computing efforts there with research in variational quantum algorithms, quantum machine learning, and error mitigation, all things that we're all very much interested in. In his past, he has had a quite eclectic career. He did his PhD at Berkeley and then postdocs at Carnegie Mellon, National University of Singapore, and University of Waterloo, where he has worked in varied things like biochemistry, condensed matter physics, quantum foundations, and practically all aspects of quantum information theory and computing. His talk today is going to be promises and challenges of variational quantum algorithms, and we're very much looking forward to hearing it. Put on the show, Patrick.
Thank you. Thank you for the very nice introduction. I'm going to now share my screen and desktop. All right, slideshow, maybe start. Okay, yeah, so I'm going to talk about variational quantum algorithms. Many of you are already familiar with them, but I'll nevertheless introduce them. I'm going to try to focus more on their trainability and their scalability in this talk. And in particular, one of the take-home messages is just to be careful. Variational quantum algorithms are not a silver bullet. Initially, we didn't have a lot of fundamental results for these algorithms, but now we sort of know better that you could run into scaling problems, and that if you're, just to show this example, if you're careful, you get the blue curve, which corresponds to large training. Corresponds to training for large scale. Sorry about the background noise. If you're not careful, you can run into a phenomenon called Barren Plateaus, where when you go to large problem sizes, you don't get any training. So just to step back, the most famous variational quantum algorithm is the variational quantum eigensolver, where the idea is that you take a Hamiltonian and you express it as a linear combination of a polynomial number of Pauli terms, and then you can then estimate the expectation value of that Hamiltonian by estimating the expectation value of the individual terms, and then classically summing them up. And the way that algorithm looks in practice is that you have a quantum state preparation that is parametrized, and then you measure the energy of your sort of guess for the ground state, and then you then use a classical optimizer to adjust the parameters of that quantum state preparation, which you then and then you loop over and over again to try to optimize the parameters of that. More generally, what does a variational quantum algorithm look like? Well, we can sort of abstractify the notion of a variational quantum algorithm, and it has this kind of general structure. So the idea is that you feed in an input state row, you have a parameterized quantum circuit, which people often call an ansatz, because ansatz means a guess for the solution. And then you have a measurement that you use to estimate your cost function. So you define a cost function that you try to minimize, and then you have a classical optimizer that you use to help you minimize that cost function. And then you then update the parameters of that parameterized quantum circuit, and you do this many times in order to minimize the value of that cost function. So that's the general structure of variational quantum algorithms. There's the reason why people like this so much is because it's so flexible. You can adjust this to any application that you may be interested in. There's many different applications, but the idea is that you adjust your input state, your ansatz, your cost function, your measurement, and your classical optimizer to suit the application that you're interested in. So it's a flexible paradigm, and sure enough, people have used it, of course, in the context of VQE. People use it for electronic and nuclear structure, but you can go beyond VQE and propose variational quantum algorithms for dynamical simulation and try to beat out sort of standard methods like Trotter-based simulation. There's also of course, proposals to use this for combinatorial optimization. So like solving max cut problems or traveling salesman problems. And that can be cast as a sort of ground state problem by constructing a classical Hamiltonian there. And finally, our group and some other groups have worked on.
When you do dynamical simulations, what do you get? The evolution of the wave function as a function of time?
Yeah, so that's right. And the idea is that there might be good ways to do dynamical simulation with shallow depth. The main issue with trotterization is that the circuit depth grows linearly with the number, with the time that you want to simulate. And so we've worked on basically variational diagonalization methods where you may want to approximately diagonalize your Hamiltonian or approximately diagonalize the unitary associated with the propagator. And then if you have an approximate diagonalization, then you can then simulate longer times with the exact same circuit depth just by changing the parameter in the circuit in the diagonal form. So variational dynamical simulation has largely been proposed to try to avoid this annoying feature of trotterization that the circuit depth grows in proportion to the simulation time. So trying to reduce the circuit depth. But it's still the same idea that you get the wave function at later times. Yeah.
But then if you're playing theoretical tricks to the pressure diagonalizations, success is very problem dependent.
Correct. That's absolutely right. So yeah, there's certain problems like Ising model where we know that there's a simple form for the diagonalization. And so the idea is that but the idea is that you might be able to find an approximate diagonalization for problems for other kind of non-trivial problems. Yeah, even if you don't have the theoretical guarantee that the exact diagonalization exists. So anyway, and then also solving linear systems of equations is another application that's come up that I'll elaborate more on. And there's been other applications proposed like quantum metrology and sensing. That's another big application that people are focusing on now. So I'll just elaborate a little bit on this linear systems one that we proposed. So here the idea is that solving a linear system, AX equals B, you want to solve for X, that's a standard linear system problem. The quantum linear systems problem is whenever you have, you want to prepare a state X such that AX is proportional to B. So then once you prepare that state, then you can do measurements on that state to then learn something about the solution to the problem. But yeah, the basic idea is you have an input. The input to the problem are A and B. We assume that A is given as a linear combination of unitaries. That's an assumption of our algorithm. And we also assume that you're given B in the form of the unitary that prepares B. And then the output of the algorithm is a gate sequence that prepares the solution vector X. And I won't go into detail about how the algorithm works, but the idea is that basically we have a cost function C that quantifies how far away AX is from B, right? Because we want, or you could say that the cost function penalizes you whenever AX has a component orthogonal to B, because you want AX to be proportional to B. And so then you minimize that cost function. There's some appropriate quantum circuit to evaluate that cost function. And then we can give some guarantees such that as long as your cost function is below some threshold, then you can guarantee that you're some epsilon close to the true solution. Anyway, that's the basic idea of the variational quantum linear solver. And but I'm just using that as an example because I want to illustrate the issue of scaling. In the big question that people ask is, will variational quantum algorithms scale well to large problem sizes? And so you could say, well, how do we even go about answering that question? Because these are ultimately heuristic algorithms. And so in practice, you can do heuristics. By doing heuristics, what we mean is that you can come up with example problems where the problem size is a free parameter, and then you can numerically look at the scaling as a function of that problem size, and then sort of surmise what the scaling might be in general, albeit examples are just examples, but that's what we have to rely on here. And so just as an example, we considered a linear systems problem where A was of the form of an Ising model. And of course, in an Ising model, you can scale up the number of spins. And so we plotted the time to solution versus the number of qubits for this simple example. And in that case, we observed linear scaling of the time to solution versus the number of qubits. Now, if you translate that into matrix dimension, of course, the matrix dimension grows exponentially with the number of qubits. And so that would be logarithmic in the matrix dimension, which would be an exponential speed up over classical algorithms. So that's good. But more generally, expanding the size of the examples to random sparse problems. So now taking the matrix A to just be a random sparse matrix, we found slightly worse scaling, but nevertheless still it was a power law scaling. So and power law scaling still corresponds to an exponential improvement over classical algorithms. So this is the kind of heuristic analysis that we try to do whenever we propose a new variational quantum algorithm. And in this case, we saw some favorable scaling. So, but whenever we analyze scaling, we have to think about all the different sources of scaling inefficiency. So where might you have scaling inefficiency in a variational quantum algorithm? One could be the circuit depth that you need to reach a good approximation of the solution. So it might just be that in order to get very close to, say, the ground state of a Hamiltonian, you need a deep circuit to do that. So circuit depth is an issue. Another issue is the number of shots that you need to estimate your cost function or the gradient. How much sort of samples do you need in order to get a good estimate of your cost or the gradient of the cost? And finally, a last source of inefficiency could be the number of iterations that you need to find the global optimum. Maybe your cost function landscape is highly non-convex and you have a lot of local minima. So maybe it takes a while to kick out of local minima and find that global optimum. So these are three different potential sources of inefficiency. And there's been work on all three topics. There's this paper by the IBM group where they found some obstacles to state preparation of ground states that in some cases you needed deep circuits to do that. There was also, in terms of the number of iterations you need to find the global optimum, there was some work on the presence of local minima, that actually training variational quantum algorithms in general can be NP hard. And so that's an issue associated with presence of local minima. And finally, the last issue is what our work in particular has focused on, which is the number of shots that you need to estimate your gradient or your cost in order to do the optimization process. And that will be the focus of my talk, but I can refer you to these other references if you're interested in these other issues. So I want to just sort of present a new phenomenon that we see in these variational quantum algorithms. Now, imagine that you want to start training your cost function, and you ask, how many shots do I need to start training my cost function? Of course, by shots I mean repetitions of the circuit, right? How many measurements do you need? And so the y-axis here is the number of shots that you need to start the training process. So to begin to reduce the cost function value by some small amount when you randomly initialize your parameters. And in this case, at least in some cases, what you find is that the number of shots that you need to start the training process grows exponentially with the number of qubits. So the x-axis here is the number of qubits, and we see exponential growth of the number of shots needed. And that's of course very bad, because that means exponential scaling. It means the number of resources that you have to put in to this algorithm grow exponentially with the number of qubits. And so, and that holds, as I show here, regardless of whether you're doing gradient descent or gradient free methods. And so the question that I'm posing is, why is it that in some cases, at least, this happens? Why is it that sometimes, especially whenever we don't think carefully, and I'll elaborate what carefully means later, but some cases we find this phenomenon and we want to understand, why does this happen? Well, I would argue that
Snelder meets super exponential. Wasn't it bending up a bit?
Yeah, no, you're right. Absolutely. For the blue curve,
yeah,
it is actually bending up. So you can even see super exponential in some cases. The gradient based method looks like it's going exponentially. Yeah. But the blue curve is going, yeah. faster.
Why are you looking at this one as a function of qubits, not as a function of parameters?
Well, because we're looking at sort of, standard algorithmic complexity kind of things. Usually in algorithmic complexity, they want to say, how does the complexity grow with the problem size? So I'm just sort of thinking of this from like a computer science perspective, not from like, imagine you didn't know what a variational quantum algorithm was, and you didn't know that they had parameters in them or something. You just want to know what's the complexity versus the number of qubits. I don't know if that makes sense.
No, but that's okay.
No? Oh,
not to me anyway, but that might be indeed because I look at it differently.
But you're an expert in variational quantum algorithms. So I think like I'm sort of imagine you didn't know that this was a variational quantum algorithm, and you didn't know that it had parameters, right? Then you would say, all right, what is the difficulty as a function of the problem size? So that's like kind of quantum algorithm talk.
This is standard. This is standard sort of like this is where computer scientists they think that how you're solving the problem is a black box, and you see how it scales with the number of qubits or bits or problem size.
I accept the answer. I just think you make it harder on yourself to do it this way. That's just my
Okay.
Like I said, I accept the answer.
Yeah. So I would argue to understand that phenomenon that I just showed you, we need to delve deeper into what the landscapes actually look like. If we wanted to plot these landscapes, want to understand, what does the landscape look like? Does it look like this or that or what? And so let's try to understand what these landscapes look like. And in one of the first papers to say something analytical about what landscapes look like is this work by the Google group, which was called Barren Plateaus in Quantum Neural Network Training Landscapes. And what they did is that they sort of abstractified the ansatz. They imagined that you had one parameter that you were interested in called theta sub k, and they called the ansatz to the left of that gate u minus, and then the ansatz to the right of that gate u plus. And then they asked, can we understand the magnitude of this partial derivative with respect to theta sub k, and how does it scale to large problem size? They considered a cost function that looks like a VQE cost function, the expectation value of an energy. Then what they were able to prove is that if either u plus or u minus or both forms a two design, then the variance of the partial derivative of the cost function scales exponentially. That is, it's sort of bounded by an exponentially vanishing function. And so let's unpack what that means. Well, what does it mean to be a two design? It means that you have a set of unitaries that reproduce averages over the Haar measure up to second order. So they sort of reproduce averages over the whole unitary group up to second order. And so it says something about the sort of distribution of the unitaries in your set. But what does it mean whenever the variance of the partial derivative is exponentially vanishing? Well, it means that you have a landscape that kind of looks like this. Whenever you go to large problem size, the idea is that the gradient or the partial derivative is exponentially small for the vast majority of points on the landscape. It doesn't mean that every single point on the landscape has a small gradient. It just means that the most points on the landscape do. And so that if you would like randomly pick a point on the landscape, if you just randomly initialize the parameters, then chances are you would end up on this flat region of the landscape where the gradient is exponentially small. And so that's what it means to have, and then people call this a Barren plateau. So that's what it means to have a Barren plateau. And now you might say like, well, what about this two design assumption? That seems kind of, abstract. But in practice, it turns out that many concrete ansatzes that people are interested in form approximate two designs. This ansatz that I'm showing here has a alternating layered structure that has locality built into it. That's useful because oftentimes, especially on superconducting hardware, you have sort of locality in your chip. And so this kind of ansatz is useful for near-term quantum computers, especially superconducting qubit quantum computers. And it's often called a hardware efficient ansatz because it sort of matches the topology of the chip. And what it is, but it's been shown whenever that ansatz has polynomial depth, that is the depth grows polynomially with the problem size, then it forms a two design. And so that sort of ansatz, which is something that people are interested in, actually is subject to the conditions of this theorem, meaning that it would have a Barren plateau whenever it's polynomially growing in size. So it does have practical implications for things that people are actually interested in. And now we can actually go all the way back to this plot that I had before, and we can understand why exponential scaling occurs. And it's because exponential precision is required just to escape the Barren plateau. The idea is that we just randomly initialized our parameters at the beginning, and we initialized onto a Barren plateau. And then we wanted to try to escape that. But in order to escape that, you have to characterize a gradient that's exponentially small. And in order to decide which direction you should go in. And so you have to expend exponential resources just to escape that Barren plateau. And so that's the origin of this plot. It turns out it's not just true for gradient-based methods, it's also true for gradient-free methods. And that's because you can show that in a Barren plateau, cost function differences are also exponentially suppressed. And gradient-free optimizers like Nelder-Mead use cost function differences to make decisions about where to proceed next in parameter space. And so then you can't make good decisions anymore whenever you don't expend exponential resources. So it impacts gradient-free methods as well. And you can even show that it impacts other optimizers like Hessian-based optimizers, because the Hessian is also exponentially suppressed in a Barren plateau, and higher order derivatives are as well. So regardless of whether you use gradient-free or gradient-based or higher order derivatives, changing the optimizer does not seem to solve the exponential scaling issue. It might mitigate it, but nevertheless, you still run into the exponential scaling. And so what that seems to suggest is that Barren plateaus is some deep result that's not easy to avoid. It's maybe like a complexity theoretic result that's telling us that certain kinds of problems are hard to solve. So, okay. So that sums up sort of the phenomenology of Barren plateaus. But then you could ask, can we understand where Barren plateaus come from? What is the mechanism for Barren plateaus? Why do they arise? And what I'll argue now is that they arise from highly expressive ansatzes, or in other words, they arise from ansatzes where you haven't put in a lot of information into the ansatz. In other words, they arise whenever you have ignorance about the solution to the problem. And what we've tried to do is connect the expressibility of the ansatz to the magnitudes of the gradients. So expressibility just means that your ansatz covers a lot of the Hilbert space, right? So expressible ansatzes means that you can reach a lot of states in the Hilbert space. So we use these measures of expressibility introduced by Alana Spiroguzic's group.
How do you define having ignorance about the solution of the problem? Because if we're trying to solve a problem, we're probably ignorant about the solution.
Yeah. These expressibility measures are meant to capture that ignorance.
Okay.
I mean, the idea is that you sort of want to input bias into your ansatz. So these are like, ignorance can also be called being unbiased. So you have an ansatz that sort of unbiasedly searches over the Hilbert space. But if you put in bias into your ansatz to selectively search over certain regions of the Hilbert space, then that's inputting potentially knowledge into the problem. So yeah, obviously it's kind of a catch-22, because like you said, you want to use variational algorithms whenever you don't have knowledge of the solution. But it turns out that you need maybe a little bit of knowledge.
And I understand that, but then you have to get it from somewhere, because you might end up, if you're only going to search certain regions, you might end up in a bad region.
Right. Yeah. So, and we can come back to that question, but it suggests that we should be inputting physics knowledge into our ansatzes, like symmetries. For example, if you have a particle preserving symmetry, or if you have a translational invariance symmetry, if you're doing a condensed matter problem. So if you can input that kind of symmetry knowledge into your ansatz, then that can be useful to avoid this issue. Yeah. So
how do you handle cases where, let's say you have a magnet, and if you put the full symmetry, you won't find the ground state because it's ergodicity break and it will order?
That's an interesting question.
Those are certain special cases. There's a lot of cases where what you're saying will work too, but there's some interesting cases.
Sure. No, that is interesting. Yeah.
Will I come back to that later?
Yeah.
At the end of the talk?
Yeah, we can come back to that. Yeah.
Okay. I'll wait for them.
So yeah. Anyway, so then so we use these measures of expressibility introduced by Alain's group, and they basically, you have this super operator A, which is looking at the difference between your ansatz, averages over your ansatz versus averages over the Haar measure, averages over the unitary group. And so, and then you can look at how that acts on the input state. If in that case, it tells you kind of the how much the ansatz is kind of spanning the producing states that span the Hilbert space, or you can go backwards in time and have it act on the measurement operator H, in which case it's sort of looking at how much the ansatz is helping you kind of reach arbitrary sets of measurements, arbitrary measurements. And so there's two different ways to quantify expressibility there. But in any case, we had a cost function that looked like a VQE cost function. We had our measures of expressibility, and then our main result was an inequality of the form where we put an upper bound on the variance of the partial derivative, and that upper bound had two terms in it. The first term in the upper bound was the standard Barren plateau term. It has in the denominator this, exponentially vanishing function, 1 on 2 to the 2n, and that's the scaling that you normally get in a Barren plateau. But then it has a sort of fudge factor or a correction factor that accounts for the expressibility of the ansatz, or in other words, it accounts for how far away you are from being a 2 design. And it's a function of those two expressibility measures that I showed you. And the idea is that this function f, it goes to 0 whenever whenever the expressibility is that of a 2 design, and but whenever the expressibility is not that of a 2 design, then the bound gets looser, and hence you have this sort of you can move off of the 2 design result and go to approximate 2 designs, and in which case you don't have as strong of a bound on the gradient. So that generalizes the Google result to approximate 2 designs, but it also conceptually suggests that expressibility is ultimately connected to gradient magnitudes. And then we investigated that further with numerics. So you could look at various ways to reduce the expressibility of your circuit, and then plot how the gradient scales with the number of qubits. So for example, one way to reduce expressibility is to reduce the circuit depth of your ansatz. So that's what this plot is showing. So it's plotting basically it's plotting the variance of the partial derivative on the y-axis versus the number of qubits. And the idea is that the variance of the partial derivative gives you a sense of the magnitude of the partial derivative. You can see that the red curve, which corresponds to a deep circuit, that's where you have the 2 design condition being satisfied, and then you have exponential decay of your gradient with the number of qubits. But then as you reduce the circuit depth, you deviate away from that exponential scaling, and in some cases you get constant scaling as you go to more shallow circuits. So certainly reducing circuit depth is one way to get you out of the Barren plateau issue. Another way to do it is to correlate parameters. So here, what I mean by correlating parameters is basically setting parameters to be the same or tying parameters together so that they correspond to the same value. And once again, we can make these plots of the variance of the partial derivative versus the number of qubits. And we can see that the more you correlate, the larger your gradients get. So the uncorrelated case is the red curve at the bottom, and then correlating with respect to qubits gets us so far, and then we get even better whenever we correlate with respect to the number of layers. So that's correlating horizontally rather than correlating vertically in the circuit. And then finally, we could correlate both horizontally and vertically, that is with respect to both number of qubits and number of layers, and then we get the blue curve, so even higher gradients there. So certainly correlating parameters is another way to boost up your gradients. And then finally, one of more obvious ways to do it is a combination of initializing near the solution and restricting the range of your rotation angles. So if you initialize near the solution, then the idea is that you're no longer in the Barren plateau, and you're more in the valley containing the global minimum. But then, of course, you don't want to just keep your rotation angles big, because then you can obviously escape that valley. And so if you restrict the range of your rotation angles, then you can kind of do this local search near the solution, and then you do have large gradient magnitudes. So restricting, you can see that when I restrict the range of my rotation angles, I'm getting larger gradients there. So there's several different strategies that you can use for how to avoid this trap of large expressibility. Any questions there? So if not, I'll move on to another question, which is, so now we know the mechanism of Barren plateaus. Now there's a question of how might you diagnose Barren plateaus? If you just have a setup and you want to know, does my setup have a Barren plateau? And we had recent work this year that connected Barren plateaus to two other phenomena, namely cost concentration, where the value of the cost function concentrates about its mean value in the landscape. And then another phenomenon that we call narrow gorges, where as you can see from this picture on the top left, it looks like as you increase the problem size, not only does the flat region get flatter, but also the valley containing the global minimum gets narrower and narrower. And in fact, you can show that it gets exponentially narrow, and that's what we call a narrow gorge. Now, you could ask yourself, like, what landscapes are actually possible? And here we show 4 different landscapes. One that has both Barren plateaus and a narrow gorge, one that has no Barren plateau but does have a narrow gorge, and then vice versa, and then finally one that has no Barren plateau and no narrow gorge. And you could ask which ones are physically possible. And the main result of our work was to show that whenever you have a Barren plateau, you always have narrow gorges and you always have cost concentration, and vice versa. So these phenomena are basically equivalent phenomena. Anytime you have a narrow gorge, you have a Barren plateau, and vice versa. So that means that the landscapes on the top right and the bottom left are actually not physically possible. Even though they're mathematically possible, they're not consistent with quantum circuits. And
that's an interesting result. Any intuitive explanation or way to think about it as to why they're not physically possible?
Well, let's see. Yeah, I mean, I'm not. Yeah, I don't really have a great explanation for that. I guess it's nature doing complexity theory or something, because if you had a narrow gorge, you could still get exponential scaling, even if you didn't have a Barren plateau, because it'd be really hard to find the global minimum. Yeah. And so, so
it might have to do that the problems might have a well-defined solution.
Yeah.
But I don't know. I'm just speculating. But it's a very interesting result.
Yeah. So then, yes, and maybe it's like you could cheat if you didn't have a narrow gorge, but you had a Barren plateau. Then maybe you could cheat and use like a big learning rate in gradient descent. But nature is saying, no, if you use a big learning rate, you'll overstep the valley containing the global minimum. Because you have
you're probably right that it's probably some complexity type of thing that makes the minimum be very, very well defined or something like that.
Yeah. So I think there would be a way to cheat. If you didn't have a narrow gorge, then you could just like do gradient descent with a big learning rate. So just take big steps. Anyway, so but what this says is that, I mean, if you want to diagnose a Barren plateau, obviously you could you could, pick various points on the landscape and then compute the gradient at every point on the landscape, and then, average it and check if it's exponentially small. But that can be costly to compute the gradient everywhere on the landscape if you have a large number of parameters. Alternatively, it's cheaper potentially to just pick points on the landscape and compute the cost and look at cost function differences. And then you can just check if cost function differences are exponentially small. And because we connect Barren Plateaus to cost concentration, then it's equivalent that if cost function differences are exponentially small, then the gradients are also exponentially small too. So anyway, so it's useful that it can be a helpful way to diagnose Barren Plateaus just using cost differences instead of gradients. So you might even say like, well, instead of diagnosing Barren Plateaus after the fact, could we just predict whether or not we're going to have a Barren Plateau based on the structure of our ansatz? And that was the subject of our more recent work, where we used tools from quantum optimal control to help us understand whether or not an ansatz is going to have a Barren Plateau or not. And here we considered periodic ansatzes, the kind of which you would see in QAOA, quantum approximate optimization algorithm. And there, the idea is that each layer is described by a generating Hamiltonian, and as is shown in this equation up here. So, and then you can look at the Hamiltonian generators of your ansatz, and then you can define an algebraic quantity called the dynamical Lie algebra, which is denoted by this symbol G. And then based on the properties of that dynamical Lie algebra, you can categorize different ansatzes as either being controllable or uncontrollable, and there's various subcategories. What we've been able to connect, gradient magnitudes to the properties of this dynamical Lie algebra, the properties of the Hamiltonians that generate the ansatz. And so what the first result is, we showed that if you have a controllable ansatz, and controllable means that the dynamical Lie algebra is full rank, then you have then that will have a Barren Plateau. And so I think this was one of the first works, or the first work that was able to connect problem-inspired ansatzes like QAOA to having Barren Plateaus. So it turns out, even if you have a problem-inspired ansatz like QAOA, you can actually run into a Barren Plateau if you have a controllable dynamical Lie algebra. But more generally, what we were able to do is connect the variance of the partial derivative to the dimension of the dynamical Lie algebra, and that's what this plot on the right shows. And we found, our observation was that the variance of the partial derivative goes as 1 on a polynomial of the dimension of the dynamical Lie algebra. So and so then that's nice, because then you can compute what the dimension of the dynamical Lie algebra would be for your ansatz, and then you can surmise from that whether or not your ansatz will have Barren Plateaus. And so I think that's a nice tool to use in ansatz design. Okay, so one of the last things I'll talk about is I've been talking about how Barren Plateaus are due to deep, sort of unstructured ansatzes that lack information content. But there's been other kinds of Barren Plateaus that have been discovered. And I'll talk about how the question of, can we extend the Barren Plateau result to shallow depth circuits? And it turns out the answer is yes, if we allow it to depend on the cost function. And we had this paper called Cost Function Dependent Barren Plateaus in Shallow Quantum Neural Networks, and where we tried to connect the cost function to whether or not you have a Barren Plateau. We considered an ansatz that once again had this brick-like structure, this alternating layered ansatz, but instead of assuming that the whole ansatz forms a 2 design, we just considered local 2 designs. So each little brick here might form a local 2 design, and that's a much less restrictive condition than saying that the whole ansatz forms a 2 design. And with that assumption, we considered 2 different types of cost functions. Global cost functions are cost functions where you non-trivially measure each qubit in your circuit, and a local cost function is where you only measure local observables. So say like 2-body observables in your cost, and so VQE problems, you often have local cost functions. Like for example, if you're doing VQE of a condensed matter system, like an Ising model, then you might have a local cost there. But global cost functions arise, especially in quantum machine learning, where people have looked at fidelities. If you're looking at the inner product between two states, then you're looking at global properties of the state. And so it tends to show up there. So people have proposed these global cost functions in the literature. And so we wanted to look at what their gradient scaling properties are. So what we found, our first result was that for global cost functions, the variance of the partial derivative exponentially vanishes whenever your circuit depth is polylog n or less. And in contrast, we found that for local cost functions, it's at worst, the gradient is at worst polynomially vanishing as long as the circuit depth is less than log n. So what does that mean? It means that we have an upper bound on the gradient size for global cost functions for shallow depth, and then we have a lower bound on the gradient for local cost functions for shallow depth. So if I was to make a plot for this, this is what it would look like. So red corresponds to having a Barren plateau, meaning an exponentially vanishing gradient, and green corresponds to having a polynomially vanishing gradient, so no Barren plateau, and yellow is like a transition region where it's neither exponential or polynomial. And so for global cost functions, we find that for constant depth or log n depth or polylog n depth, we prove that you have a Barren plateau. And then when you combine that with Google's Barren plateau result, which holds for poly depth, then you basically find that global cost functions have Barren plateaus for essentially all circuit depths, and hence they're bad. So these are bad cost functions to use. In contrast, local cost functions have a trainable region for shallow depth. So whenever you have constant depth or log n depth, local cost functions have polynomial vanishing gradients. That means that you only need to expend polynomial resources in order to measure them. Of course, you still have the Google Barren plateau result when you go to poly n depth, but at least there is some shallow depth trainability of local cost functions there. And we saw very clear evidence of this phenomenon in our numerics. We looked at a quantum autoencoder problem. This algorithm was proposed by the Zapata group, and what we did is we considered two different cost functions. One was a global cost function, which is shown with the red curve. The other is a local cost function, shown with the blue curve. And here with each panel, we're increasing the number of qubits by 5. So 10, 15, 20, 25 qubits. And we can see that up to 20 qubits, both cost functions are trainable. So if you just did heuristics up to 20 qubits, you would say, all right, well, everything looks all good. But then as soon as you get to 25 qubits, and then all the way up to 100 qubits, the global cost function is completely untrainable. So we just get a complete flat line, and we're not able to reduce the cost function at all for the global cost. In contrast, the local cost is trainable for all problem sizes that we considered, all the way up to 100 qubits. So that illustrates that local cost functions are obviously better than global cost functions. Now you might say, well, but can you always use a local cost function? And in many cases, it turns out you can. We were able to show that our local cost function is faithful. It vanishes under precisely the same conditions as a global cost. And what that means is that if you manage to directly train your local cost, you're also indirectly training the global cost. So that's sort of what we propose to do, is directly train your local cost, which will drag down your global cost as well. Okay, now there was a really nice implication of this work that was elucidated by Jacob Viamonte's group in Moscow. And what they realized is that when you're doing VQE for condensed matter systems, you have the option of using different fermion-to-qubit mappings, like the Jordan-Wigner transformation or the Bravik-Kitaev transformation. But these different transformations, when you actually lead to different kinds of non-locality in your Hamiltonian. It turns out that the Jordan-Wigner transformation leads to more non-local terms in the Pauli representation after the transformation, whereas the Bravik-Kitaev has more local properties, more local Pauli terms. And they could really see this show up when they plotted the partial derivative scaling, right? So they're plotting here the variance of the partial derivative versus the number of layers. And they find that for the Jordan-Wigner transformation, which has non-local terms, you do get this Barren plateau for shallow depth, whereas in contrast, for the Baravi-Kitaev transformation, you don't get that Barren plateau for shallow depth. And so I thought that was a really nice illustration of our results, because it shows that, you know, it can help you guide which fermion-to-qubit mapping you choose in VQE.
But that is by design, right? I mean, the transformation is designed to either spread well, there's two portions of information. It's the number and it's the parity. And for the first case, this is what you expect. But then how is the connection between that single piece of information getting this result? Because it's not.
Sorry, can you repeat?
Baravi-Kitaev gives you a different trade-off between how you encode the information of parity and the information of the number of fermions that you have in the system versus Jordan-Wigner, but it's still the same information. And basically, the question is it the information being spread out, or is it the structure of the circuit that gets produced that causes the behavior to be like it is?
So, well,
we have the same problem with running optimization tools on the produced circuits. That in the case of Jordan-Wigner, it gets completely stuck.
I see.
And I'm kind of curious whether, because a lot of the optimization that we do in the circuit optimization is also just a normal optimizer. Sorry for the double speak of the word optimizer, but the whole similar problems occur there in choosing the circuit layout is very, very similar to the problems that then happen at the level of the actual VQE algorithm. And so I'm kind of curious whether there's a connection there.
Yeah. So I will say that our analysis was for a specific kind of ansatz, these hardware efficient ansatzes where you have these alternating layers.
Yeah, but those don't matter. Those don't matter. It's really the mapping that causes the spread of the information. It's by design.
Yeah. So yeah, I'm not sure I entirely understand your point, but I think that they were, you know, I mean, really just, they were, in their paper at least, they were arguing that this is, you know, consistent with our results, that because just if you look at the Hamiltonian itself after this transformation, then you have, you know, more kind of global polystrings.
Yeah.
Right. Like you said, I guess, spreading out the information.
Yeah, I mean, you get these curtains of CNOTs in the case of Jordan-Wigner, and the other one produces star-shaped clusters.
Yeah. Okay. Yeah. So yeah, I mean, I only have you know, just one more slide, so I'll just conclude by saying that Barren plateaus are one of the few complexity theoretic results that we have for variational quantum algorithms. So I think they're exciting and interesting. They can determine whether or not quantum speedup is possible, because they can lead to exponential scaling, which you were otherwise trying to avoid with a quantum algorithm. And we've connected trainability to expressibility of the ansatz, or controllability of the ansatz, as well as locality of the cost function. I did not discuss other mechanisms for Barren plateaus, like entanglement-induced Barren plateaus, which was related to the fact that you generate a lot of entanglement in your circuit, and also noise-induced Barren plateaus, which are due to hardware noise, but those are also important issues as well. And it certainly suggests that strategies to avoid these things are a crucial area of research. So with that, yeah, thanks very much, and I'm happy to take some further questions.
Yeah, let's thank Patrick for his talk. And yeah, anyone who has questions, please go ahead.
Yeah, I have a couple questions. The first is that, so I mean, we talk about these issues impacting a given quantum circuit, but the decomposition of that circuit is not unique. So is the assumption here that if you were to decompose the same unitary operation into a different circuit containing different single qubit gates, would the landscape look the same?
So if you, okay, so first of all, I'm just going to ignore noise, because if you have noise, then certainly it sort of differentiates between different decompositions, right? So I would say noise definitely breaks the symmetry between different decompositions. But ignoring noise, then assuming that then it shouldn't change the landscape, as long as you're not just, as long as you don't like introduce new parameters by decomposing in different ways. It shouldn't change the landscape. Yeah, there. I mean, it's possible that maybe when you decompose, you decide to add more parameters or something because you introduce new gates, in which case you change everything. Yeah, but I think it shouldn't change the results. The two design results, yeah, are just properties of like global properties of unitaries. So, or sets of unitaries. So then it's not taking into account the local decomposition. So then in that sense, it's ignorant of the decomposition. Yeah.
Yeah, and my second question is, if you were to try and restructure the noise of your landscape, say by twirling over a group, does this make trainability harder or easier, or is it kind of a wash?
That's a really good question. And yeah, so noise-induced Barren plateaus, we had a paper about this recently, and I mean, twirling almost certainly will not, I mean, okay, it won't get rid of this noise-induced Barren plateau issue, but it could get rid of other issues, which is noise can not just flatten the landscape, but also corrupt the location of your global minimum. And you could end up learning the wrong parameters because of noise. So, it turns out that for certain types of noise, like depolarizing noise or global depolarizing noise, then you can oftentimes prove that you have noise resilience in the sense that the location of your global minimum does not shift in parameter space. But for other complicated types of noise, you don't necessarily have that result. And so you might end up learning the wrong parameters whenever you train. And so noise can take you to sort of the wrong spot in parameter space. But your twirling idea could resolve that issue if you can twirl to make the noise simpler or more like depolarizing, then that could help you learn the correct parameters. Yeah.
Thank you.
Can we go back to the expressibility? I have another open question. We actually discussed this morning. So I completely agree with everything you said in terms of getting towards that valley. But now assume that we reach the valley and we're all the way at the bottom, close to the minimum. And now we want to get the best accuracy possible. And then it goes basically to follow up to do what David said. If you have more information of the physics there, the question is, does it then make it harder or easier to find the actual global minimum, the actual state that you are? Because there's two trade-offs. One is you are flat. I mean, this is the minimum. This is where you're going, and the reason you're flat is because this is the answer that you chose, and the only way that you can get to the global minimum is to follow states that have physical meaning for your problem. Whereas if you were to search the full Hilbert space locally around that area, there's more ways of getting to that global minimum, although the states that you might return back may not be ones that make sense for your calculation.
Mm-hmm. That's an interesting idea, that like if you get close to the region and then it's hard there, whether you search more widely there, whether a mix of strategies might help some problems.
Yeah.
We had a big argument this morning for like half an hour. So I'm just completely interested in what your opinion is.
Yeah. I mean, well, yeah. So what we found is that like, if you like, it doesn't make sense to restrict the search space if you're really far away from the global minimum, obviously. But if you do happen to be in the region of the global minimum, then it really absolutely makes a difference to restrict the search space, because then you potentially
the ansatz is the question.
What's that?
Yes, it makes sense to change the search space. This always makes things easier, but to remove the ansatz on your talk to make it more expressible. So to remove physics constraints.
Oh, right.
Once
You
you're close
need to
enough.
make steps in physical. The ansatz only allows you to select points that have physical meaning for your model, which gives you a certain path to get to that minimum. But now you're close to the minimum, so everything is flat by definition, because that's by design, right?
Yeah.
So
I know what you're saying.
What
now.
if I mess things up? And then would it make it easier to get to where I wanted to be if now I say, okay, and make it more expressible, and therefore I do what I'm in search space, but because I restricted it, it's not that bad. And so maybe now I can get there faster.
No, I agree with that. I generally agree with that intuition, and we've been thinking about that as well. You can also call it pre-training, right? Like if you manage to, you could pre-train with a sort of low expressibility, and then like grow the expressibility later on. And the idea is just that you don't want to hit the Barren plateau at the very beginning. So you want to avoid the Barren plateau at the very beginning by having a low expressibility ansatz, and then making progress in training the parameters. But then once you have better parameters, then you can feed that into a high expressibility ansatz, and now you're violating the assumptions of the Barren plateau theorem, because you're no longer doing random initialization of your parameters. You're putting in a special kind of set of parameters, and so then you could potentially, smoothly transition and possibly never hit the Barren plateau, by doing it.
My question is on the potentially and the possibly. I mean, do you ever feel how potential and how possible?
All I can say is we're thinking about this as well, and we don't have an answer yet. But we are actually. I mean, we may even want to talk to you guys outside of this, because we're trying to think of good pre-training methods that can scale. And there's pre-training to avoid Barren plateaus. There's also pre-training to avoid local minima as well, because some kinds of ansatzes avoid local minima too. So you could potentially pre-train with a landscape that has no Barren plateaus and also no spurious local minima, something like that, and then initialize into a landscape that has Barren plateaus and local minima, but you've sort of bypassed those, I guess. Yeah, it's a good idea. It's something we're thinking about actively.
Okay, let's thank Patrick again, because we're a little bit over. This was very interesting. Thank you, Patrick.
Thank you. Yeah, thanks for the really good questions. I appreciate it. So